So guys, the last few lessons was on modelling linear growth and decay, and then we went into the nth term of linear growth and decay.
And determine a rule using the nth term.
Yep, and now we're going to do modelling geometric growth and decay, and then we'll do the nth term for geometric growth and decay.
Which is in the next exercise.
Like linear growth and decay, geometric growth and decay are seen commonly around the world. And our biggest example, Miss, would be?
The coronavirus.
There you go.
So, everyday examples, and particularly those that we'll be focusing on here for our use, include the use of compound interest, which is different to simple interest, and we'll also look at depreciation, which is not a flat rate of depreciation, but rather what we call reducing balance depreciation. So, we still need to establish a recurrence model, just as we did for linear, but this time for a geometric sequence. So, when that is the case, we need a starting point, just as we did in the previous ones, and we need to see if a quantity is increasing or decreasing, what are we doing to that? So obviously in this case, because we're not adding or subtracting, because that would be linear, we're actually multiplying by a percentage of something. So in the first example, recurrence relation there, we have a starting point of 1, so VO equals 1, and it tells us that we're able to generate our next term by multiplying 3 times the previous term. And because our previous term was 1, we know that our next term there would be 3. If we kept that going to get the next term in our sequence, we would be using that answer, timesing it by 3, and we'd end up with 9. If we continued that again, we'd be saying 9 times 3, or 3 times 9, to get 27. So we're using the previous rule. So this is an example of modelling. If you have a look at the next one, we're doing the same sort of thing. We're starting here with 8, but this time we're multiplying by, again, a percentage of something. So in this case, it's 0.5. So we're saying 8 times 0.5, which is 4. That was our first term. The next one would be 4 times 0.5, which in that case would be 2, etc. And we could continue to generate that sequence. So both have rules and follow those rules that really are a geometric pattern. And if you have a look at the table below, it shows us what that looks like graphically. So in that particular case, we started here, and in that case, we had when x was 1, our y value was equal to 3. If we kept multiplying by 3, which is what the rule is telling us to do, we no longer have a linear relationship there because we're not adding the same amount or taking away the same amount, but we're multiplying. So you see how it's a curve? We call that, in this case, geometric growth. If you have a look at the next example, we end up with geometric decay, and if you have a look there, we have the values are decreasing. And if you have a look at what we're multiplying by each time, because the first rule we were multiplying by 3, which was a number larger than 1, we had growth. When we're multiplying by a value that is less than 1, we end up with decay.
So when we're talking about the coronavirus at the moment, guys, this is what's happening with us. We're heading towards a peak, and then it starts to flatten out, and hopefully we get to the stage like that. Look, you've got your parabola. Close your eyes, parabola.
Okay, so that just gives us a rule for R. R in this case is our constant. If you remember, we used D for linear. We use R for geometric relations.
We're still using the VNs, but
Yes.
R and D as the two difference for geometric growth and decay. And again, looking at this is when you know if R is greater than 1, is growth. If it's less than 1, it's decay as well. Compound interest, investment, and loans.
So most of our interest calculations are not as simple interest. We more frequently use compound interest, where interest is earned depending on how long it is in an account, for example. So for compound interest, it's important to know the principal, so what we started with in terms of our either investment or our loan. So the amount that we start with, we need to know the period of time it's there, and we also need to know the rate, because each of those bits of information form our formula, which are going to allow us to calculate how much we have in an account by the end of a particular period of time.
So I just want to mention, Miss, compound interest, the difference between compound interest and simple interest. Now, simple interest, when we invested $2,000 at 10% for 1 year, 10% of $2,000 is $200. So at the end of the year, how much would I have in my bank account? $2,200. Compound interest will give you interest on the $2,200, but simple interest will never give you on $2,200. It will give you on the original amount only.
So the interest on simple interest is always the same. In that example, it would always be $200. For compound interest, the longer time it was in the account, the more interest it would earn each time.
So in the second year, I'd get $2,200.
That's right.
Why not?
Because the first one, simple interest is...
Sorry, $220. So
Simple
in my
interest
account is $2,200 in my account. I'd get $220 as interest at the end of it.
Yes. So simple interest is linear. Compound interest is geometric.
Beautiful. Okay, so for compound interest, let's consider this investment of $5,000 that pays 8% interest per annum, compounding yearly. Now, we'll talk about compounding yearly, monthly later on, but at the moment, compounding yearly. This means that the investment's value increases by 8% each year on what is in the account at the end of the year after the interest has been paid. Okay? So we'll model it like this. Let Vn be the value of the investment after n years. So then we can write that our initial investment is $5,000. Each year the investment will increase by 8%. So V of n plus 1 equals capital R times Vn, where this part, guys, 1 plus R on 100 is your capital R. That's what it stands for, and that's your Vn there. So what happens in this situation is we've got 1 plus 8 divided by 100, and that's where this 1.08 comes from, times Vn. So that's the compact way to do this relation. So now we can use this rule to model and investigate the growth of investment over time. So we already spoke about the difference between simple interest and compound interest, and we use the rule that we've just written to you before. So V of O is your principal amount. So you use this rule for compound interest, please. So
and you can see that that's a relation recurrence where it has the two parts, and that's essential to ensure that you keep using that. So let's have a look at this example where we have a recurrence relation that is modelling a compound interest investment of $2,000, which is invested at a rate of 7.5%. So first of all, we look at what we've got, which is our...
So Miss, here they've already given us the recurrence relation, so but how do we get this 1.075?
Well, we'd be looking at working out what capital R is. So capital R we know is 1 plus little r over 100, and in this case little r is 7.5, so it's 1 plus 7.5 over 100, which gives us capital R, which is 1.075.
Great, so that's how we do that. So then the questions are, use the recurrence relation to find the value of the investment after 1, 2 and 3 years. So they want V1, V2, V3, starting from 2000. And then determine the value of the investment when it first exceeds 2,500, and write down the recurrence relation if 1,500 was invested at a compound interest rate of 6% per annum. So they're changing these up a bit. So now we'll move on to a step-by-step approach.
So in this case, we've got V0 is $2,000. V1 would be R times that amount to give us $2,150. Then we would use that answer and times it by R again.
There it is there.
And we keep doing that. And these are the one by one steps and iterations that we would be working through as we did with linear, where we were just pressing enter each time once we'd set it up.
So you've got the graphics calculator steps in the previous videos. Again, you would just put enter 2000 into there, then times it by 1.075, enter, and then you keep pressing enter and it will generate that sequence there for you. So then you can just answer the question here. After 4 years, the investment will first exceed 2,500. When does it exceed 2,500? Right there, it exceeds it because that's still there. So that's 1, 2, 3, 4 years, and you just count it from your screen. Very simple and straightforward.
So it's after 4 years that it goes over that 2,500.
Yeah. And then that last question was write down the recurrence relation if 1,500 was invested at a compound interest rate of 6% per annum. So again, it's just redoing the whole, you've got to get the relation first, the rule.
Yeah, you'd have to work out capital R first.
So the capital R is 1.06. So that's, instead of using 1.075, that's our initial investment there. So it's 1.06 times 1,500, and then you can generate a sequence based on that as well. Next example.
Okay, so here we've got someone who's borrowed $5,000 and will pay interest on that at a rate of 4.8% per annum, and N is the number of compounding periods. Now, this is where we start to have to look at some changes because 4.8% is per annum. That's your rate for the year. But if it compounds more regularly than just once a year, that can have an effect on in this case, our loan.
So guys, if you have a look here, it says 4.8% per annum. It says write down a recurrence relation to model the value of Brian's loan if interest is compounded yearly, quarterly, and monthly. So yearly would be the full 4.8% per year. Quarterly, what do you think happens here if that's per annum? What do we have to divide it by there to get that rate? It'd be 4.8 divided by 4. And then monthly would be the 4.8 divided by 12 because there's 12 months in a year. So what you've got to look at is you get interest yearly, you can get interest quarterly, and you can get interest monthly, and banks also provide daily as well. I don't think they do weekly. Do they do weekly? Sometimes they do. No. So now let's have a look at the way to generate this. So we have to generate this. So let's go look at yearly first. So the interest rate is 4.5% per annum. Remember, big R is 1 plus little r on 100. That's what we're going to use to model for yearly. So the initial value of the investment was 5,000, and it will look like that. All they're asking for at the moment is to model it, and that's it.
Just a rule.
Right? So that's that one. Now we're going to do quarterly. So the interest rate is 4.5% per annum divided by 4. What do you think's happened here? Look, guys. 1 plus r on 100. We've got to use this now for that, and that number there is the next one. Then, to do it for monthly, exactly the same steps as before. We're dividing by 12. We've got this, and our new recurrence relation is this for monthly.
So what changes there? Your little r is being divided each time by something. In the first case, because it's per annum, yearly, you're only dividing it by 1, so it doesn't change it. But in the second one, you divided it by 4. You said 4.5 divided by 4 divided by 100 and then added 1. So you had a new R value. So that has changed in your rule. And for the third one, for C, you did the same thing, but your little rate was being divided by 12 because it was a monthly compound interest period.
Okay, so the next part is reducing balance depreciation. So don't forget, earlier in the chapter we studied 2 different methods for depreciating the value of an asset, both of which were examples of linear decay. So reducing balance depreciation, very important word. Reducing balance depreciation is another method of depreciation, one where the value of an asset decays geometrically. So don't forget, it's non-linear now. Each year the value will be reduced by a percentage, whatever it is, of the previous year's value. The calculations are very similar to compound interest, but with decay in value rather than growth. So it's not growing here, it's going down, because an investment was growing, now it's decaying, it's going down. So we're going to have a look at the rule. So exactly the same rule as before. What changes is in R, it's just 1 minus R on 100. Exactly the same rule, so don't confuse those two. If it's decaying, it's the 1. So it's the same formula as before, but it's replaced with a minus instead of a plus. Example. The following recurrence relation can be used to model the value of office furniture with a purchase price of 6,900, depreciating at a reducing, I always underline reducing balance so I know what I'm doing, at 7% per annum, and they've given it to us right there. Again, where did the 0.93 come from? 1 minus little r on 100, and in this situation that was 7. So when you do that, you get 0.93. So then it goes on again in the recurrence relation. V of n is the value of the office furniture after n years. Use the relation, so exactly the same sort of question, but with a minus. 1, 2, 3 years, determine the value of the investment when it will be first less than 5,000. Again, graphics calculator, do it 5 times, press enter, you get your answer, you count how many years. So on the graphics calculator, again, you can generate this whole sequence by typing in 6,900, enter. Then, remember when you press enter, you can just do times 0.93, will give you ANS. Your calculator will give you ANS. Then you put in times 0.93 and then keep pressing enter and you get to this. So then, Miss, the question says the value of the furniture drops below 5,000. 1, 2, 3, 4, 5. 5 years, it drops below 5,000. And that's it.
Done.
So have a go at doing 8E or questions.